Amen.
Have to um, just in case it starts working. Okay, testing. Do you think it's working on here? Like, we should get testing. Yeah. Okay. Yes. Yeah. Let's. Okay, sure. Let's wait just another minute or so. Why is it all? No, let's wait a few more. Why is it all? Yeah, you can't do anything about it. It's the ball. Something like last time. No, it's fine. We're gonna shoot. So we need to take a few. Yeah. Yeah, sure. Okay, we can probably get started now.
Hey, welcome to the U of T Computer Vision Club event. And so we originally had this event in another room, but we couldn't figure something out. Um, so the club is sponsored by U of T Student Life as well as GitHub. GitHub also has this thing called a student developer pack, so you get a bunch of benefits for free if you're a student affiliated to an academic institution. So feel free to take a look at this if you want to. And we are a student club for computer vision and machine learning here. And today, Alex will. Usually, we do all of these paper discussions for very recent papers, like 1 week ago, 2 week ago, and so on. Today, Alex will do a much more in-depth breakdown of uh, what I would call like a fundamental paper in the field, or super influential paper in the field. Uh, and also uh, we have a sign up sheet there that U of T requires us to fill out. We didn't used to have that up until now, but U of T asked us to have like some kind of sign up sheet, so do fill it out. And also, if you're hungry like me, lunch is on its way, and probably blame the delivery drivers. Alex.
All right, hi everyone. So let's get started now. We're first going to start off talking a little bit about point clouds and some different representations of 3D objects, and just try to get some geometric intuition for the kind of models that we actually want to train. So who here has heard of a point cloud before? Yeah, okay, pretty common data set or way to represent a 3D object. And can anyone tell me maybe how we might collect point cloud data in the real world, or where it might come from? Yeah. LiDAR? Yeah, exactly. So that's my next slide right here, is an example of LiDAR used for a self-driving car. So if you don't know what LiDAR is, or you're not familiar, basic premise of how it works is you shoot out a light ray, you detect that coming back, and then you're able to sense depth for all sorts of parts of your scene and depth at a particular point, which is what gives you a point cloud, or just a set of points in R3. Here's an example of what we might want to do when we're learning on these point clouds. So you can imagine for self-driving, there's several different pipelines we might want to have and objectives we might want to have. Here's one example, is semantic segmentation of our scene. So we color our trees red and our buildings yellow, for example. And there's also a lot of interesting questions we can ask when we're performing learning with point clouds. So let's say I'm designing a self-driving car and I want to ask, oh, maybe I want to use a regular camera where I just get images, or do I want to use something where I get these point cloud structures? You know, do point cloud structures give me more information? Am I able to extract more information from my image than just detecting cars and where things are if I have a sense of depth? Or maybe if these point clouds are very sparse and we can't detect these fine-grained details, like the cars in the image here versus just the boxes in our image to the left. So there's a lot of interesting questions we can ask when working with point clouds. Point clouds do come with a couple of problems. So for example, sparsity, partial view, or occlusions. You can imagine, let's say I'm detecting a car that's over here, and I have my sensor that's over here, but the car is around a corner, so only the front part is sticking out. I want to still be able to detect that is a car. So if I have a point cloud and I cut it in half and get rid of half of the points, how am I able to still deal with this? So point clouds do give us sometimes richer representations of our scenes, but they come with some trade-offs in how good our sensors are. So we're going to start off with a simple problem, which is just object classification. So instead of doing something complicated like sensing an entire scene and then segmenting it, or something like self-driving, let's think of a simpler problem where we just have a bunch of points and we want to classify what these objects are. So one question we can ask, which is going to be the main focus today, which is what kind of properties should our function have? Let's say we have a learning algorithm or a neural network. What should we be able to say or guarantee about this network? Does anyone have any ideas? So I'll give you a hint. Any ideas? Yeah, so maybe if we rotate our point cloud, if I rotate this chair a little bit, is it still a chair? Maybe. Another one we can focus on is, well, I need to actually feed these points like consecutively or in some kind of order to my network. So this, you know, what happens when I say permute this order? You know, so if I enter all these points in from, let's say, lowest x value to highest x value, what happens when I flip this around and go from highest x value to lowest x value? The permutation of our points that we use as input to our network shouldn't have any effect on semantics. Everyone kind of understand that? And we can also look at other like simple transformations as well, like say a translation in space or a scaling in space, you know. So if I take this chair and I just multiply everything, all the points by 2, well, it still looks like a chair, right? It's just on a different scale. So how can we start building up in variances to this kind of geometry? Another interesting question is, when do we not want to have some invariances? Can anyone think of an example? Maybe here's a hint. So before we said, okay, we have this rotation that should change the meaning of our object. But here you can see I have this up arrow, and if I rotate it, I get a down arrow. So the invariances that we need are application specific, and you need to deal with this on a case by case basis and ask yourself, like, do these actions change the semantics of what we're working with? So in the case of a chair, if I rotate a chair, it's still a chair. But in the case of the arrow, you could have some very big problems. So here's an overview of some potential desirable symmetries that we're using. If you know some group theory, we have some fancier language right here to describe exactly what we were talking about before. So rotations, reflections, scale invariance, permutation invariance. Some things we didn't quite touch on is invariance to noise. So going back to this idea of LiDAR and sensing our scene by shining out a light ray and detecting what comes back, this is a measurement in the real world. So there's naturally going to be some noise in this measurement. So for example, let's say I had a perfect point cloud of this cube right here where all the points were lined up on these black lines you saw here. And then I just pointwise add some Gaussian noise. I'll get something like this. It's clearly still this cube shape. It looks very much like a cube to me. But how can we guarantee that our model would still be able to reason about this noise and classify it as a cube? We also have some different kinds of noise in the form of outliers. So let's say I have really good representation and really good measurements, but I might have some points, like artifacts we might detect in our scene, where one point on the cube is randomly over here for some reason. We need to be able to deal with this as well. And one last thing that I'm not going to touch on for the rest of the presentation, but an important consideration to make is what other data do we have aside from our points as a representation of our scene? So for example, imagine we had a 3D sensor where we're not only able to calculate these points in our scene, but we're also able to get a color value for that certain point. Or let's say we care a lot about like this local orientation of the objects that we're working with. So we get some surface normals where instead of, say, representing my image as just a point cloud and then converting this to a polygonal mesh, we might need some finer grain information, like the surface normals corresponding to a particular point. You can see here, that's how we get this wavy shape instead of what would otherwise be maybe just a bunch of polygons. All right, so there's a lot of symmetries we need to consider, but what we're going to mostly focus on for now is permutation and variance. So everyone's, just to make sure before we go forward, everyone's clear on what that means? Yeah? Okay, can anyone give me an example of something that's permutation invariant? So I'm looking for a function that takes in any number of points and gives me, let's say, just a real value. And no matter how I permute my inputs, I still get that same value. Yeah. Yeah, that works as well. Or just sum all of the inputs. Yeah. Again, because we're dealing with just arbitrary length, you might just say sum all of them. Another one too is here on this slide, max pooling. So you can imagine if we just take max just element wise of all of our vectors, we're still going to get the same thing no matter the ordering that we feed max in as input. Right, so the paper says we show that our network can approximate any set function that is continuous. But if we have a function that is, let's say, permutation invariant, does this make any sense? Does it seem like there's a contradiction here? So something we can think about a bit more as we go forward. Okay, so a problem statement. So we're dealing with two kinds of problems in this paper. One is object classification, like we've seen, and the other one is semantic segmentation. So let's say I want to segment every single point in my image into M categories, or let's say 3 categories. So maybe roads, trees, and buildings, for example. So what I'm going to have is, let's say, just a binary matrix output where when I feed in n points, I'm going to have an n by m matrix where maybe there's a 1 if it corresponds to, let's say, a tree in the tree column or the tree row, and there's a 0 if it doesn't. This kind of makes sense to everyone. You can also imagine going forward, because like that's typically used in these classification problems, this might not be exactly a 1 or a 0, but it might be a probability, like a 0.9 chance that this is a tree or a building. And then to separate these values, we might just say, okay, if there's a 0.9 or a 90% chance that it's a tree, 5% chance it's a road, 5% chance it's a building, or we're going to pick tree. And then this would give us this binary matrix representation. Yeah. Sorry?
So you consider volume point clothes as in if you had a cube, everything in the cube should have approximately a line in the center, or should it be the surface of the cube covered by the same?
This is only considering volumes because it's doing classification into n subcategories by every single point. Yeah. Okay, so now we're going to focus on our PointNet architecture. This is the main figure in the paper. So you can see the same problems that we're solving here are classification and our segmentation network. Segmentation, we're not really going to touch on in this presentation, but I'm going to do a deep dive into classification. And then after, if you kind of understand, you should be able to go read segmentation on your own. Okay, so the authors say our network has 3 key modules: the max pooling layer as a symmetric function to aggregate information. So max pooling, or just a summation like we saw, is what might be able to give us permutation invariance. It says a local global information combination structure. So this is not going to be used so much for classification, but that's this part, the beige here, for segmentation. So we don't need to worry about that too much. And 2 joint alignment networks that align both input points and features. So some stuff between here. All right, so let's start off to see how we can guarantee something like permutation invariance. So we have one option, which is sorting all our inputs into a canonical order. So let's say I have some pre-processing where I'm given some arbitrary sequence, and then no matter how I permute that, it gets mapped to a representation that's, say, of the same sequence length. So we would say that this gives an order to our vectors. The problem with that is that it complicates things when it comes to like perturbations, especially when we're in very high dimensional spaces. So perturbations, what we were talking about before, is we have all our points, like the example in the cube, and then we add little bits of noise to these points. Ideally, we should still be able to classify it as a cube. You can see this mathematically. I can touch on it a little bit more after. I'm not going to go into the details for why this messes things up right now, but it's actually quite clear. Right, sorry. So next, we might want to train on multiple permutations of the same point cloud. So one easy way to learn permutation invariance is, let's say we take our data, all our data, so all our point clouds that we train on, and then we take every permutation of that, and then our data set just grows and becomes massive, and then we train on all of that instead. Usually in practice, to make this tractable, we would just take a few permutations or take a new random permutation for every batch or every gradient descent update. This is how some people deal with this too. But we're after something a little bit stronger in this paper. Is how do we actually guarantee that our network is permutation invariant? So not that we just have good validation laws that shows that we usually have permutation invariance, but how can we actually guarantee this? How do we know that the function that we learned is permutation invariant? Right, so this is the approach taken on the paper. And one other important question to ask yourself is, when we aggregate all our information in the end with something like a summation or max pooling. We're just taking max element wise of through all of our vectors. How much information are we losing? And does this affect the expressivity of our network? Right. So the authors make a very interesting argument here. Is they say that for some function f that should satisfy all the things we want, it suffices to just use a symmetric function g and then apply function h pointwise to each of our individual vectors. I'll give you a minute to just read. Right. So let's see how the authors actually go about doing this. So first, we're going to apply an affine transformation given by the output from a TNet. So a TNet, just think of as just black box it for now. So a TNet also gets input from our previous layer. So it gets n of our three-dimensional vectors. And what it's going to output is it's going to output an affine transformation. So you can think if this is like linear instead of affine, it's just going to output a 3x3 matrix. And we're going to apply this 3x3 matrix to every single one of our points. We're going to apply it pointwise. Okay. Next, after this, we're going to take a regular multi-layer perceptron and we're going to apply this multi-layer perceptron, again, just pointwise. What's interesting here is we're mapping to higher dimensional space. The reason why we're mapping to a higher dimensional space is ideally we will need a higher dimensional vector than something that's just three-dimensional once we choose to aggregate all of our information. So you can imagine if we sum a bunch of three-dimensional vectors, we might be losing tons and tons of information because we're just get back a three-dimensional vector to represent n three-dimensional vectors. But if we end up mapping to something like a 64-dimensional vectors and then we aggregate, maybe we don't lose as much information. Next, we're going to do the exact same thing again, is use our black box TNet, and we're going to apply an affine transformation to this previous output. And then we're going to map to even higher dimensions right here. And up until this point, you see we just have an affine transformation dependent on our input. So our input over there. And then we're going to apply fixed pointwise multi-layer perceptron here. We're going to have an affine transformation dependent on our input as it's right here. And then we'll apply fixed pointwise MLP again. Now we're about here. So now what we've done is pointwise, we found a way to just map n three-dimensional vectors to n 1024 dimensional vectors. So now you can imagine we have a richer representation where we're not losing as much information when we aggregate all of this. So when I take max over something that's 1024 dimensional, maybe this should be able to preserve more information than if it was just three-dimensional. Of course, you know, if n is very, 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 very large, this is not going to work regardless, but usually you should be able to then just scale up 1024 to something that's problem specific. Right, so now we do exactly what we were looking at before, is we perform symmetric aggregation. So we aggregate these vectors in a permutation invariant way that just uses max pooling. So this is just element-wise max over all of our vectors. And then we have k-dimensional classification output. Can someone guess the function that we use for this? Softmax. Okay, and does anyone know any interesting properties about softmax? True. So it's the reason why we would use it for classification. And then maybe if we want to classify it out of our k-dimensional things, we'll take argmax of that. but I'm looking for something to do with invariance. So we're looking to construct an entire network that's completely invariant to permutations. So let's say our network was invariant to permutations up until this point. If I take softmax of that, will that be permutation invariant as well? Or I'll give you a hint. If I take any function of that, will it be permutation invariant? Well, yeah, because what we've done is we've taken our input from way over there. Let's say it's permutation invariant up to here. So no matter how I permute my inputs over there, I get the same input to softmax here. So then I take softmax of that, and you can see our entire network is permutation invariant. Clear? Yeah, it's simple. Maybe you're yeah. So now you can go back to this diagram and you can see maybe this makes sense. A little bit more sense. So we can approximate this function f with these h's and these g's, where you can see these h's are just applying transformations to each input vector. So over there, when we take our affine transformation, we apply a transformation to each input vector individually. Over here, we apply one each individually, and then we aggregate. So can anyone kind of see what is H and what is G? Does anyone have any ideas? It's part of it. It's part of it. You're getting closer. You can even just read it again. So where do we stop transforming our points point-wise? Yeah, exactly. Does everyone see that? Is that clear? Just before max pooling. So you can see here that, well, this is probably G. This is probably H. So now we can work with, instead of working with this network and trying to prove some properties about it, we can deal with something simpler, like this representation right here, mathematically. That's clear to everyone? Still in the paper, we're gonna have to actually make use of max explicitly, but we'll get to that in a minute. Yeah.
I'm just curious, the affine transformation, what is that? Normalizing, is it link permutations, is it rotating, like what is it? And
Yeah,
it's the same,
this-
and
this-
how do you determine that function?
Yeah, so this is a great question. So I left this purposely ambiguous
Okay,
now
sorry.
for like gotchas later. But I can dig into it a little bit right now. Maybe for now, I'm just gonna say you're clear on what an affine transformation is.
Well, thinking it potentially could do any one of those things, like
Yeah.
it could be rotating. It
Yeah.
could be doing, it could be twisting or, yeah.
Yeah, so an affine transformation is a linear transformation that's then translated, or possibly not translated if you translate just by the zero vector. So you can imagine it can be used to, this is maybe a hint for later, used to help learn things like translation invariance or rotation invariance. You have exactly the right idea, is maybe these parts of our network right here should be used to encourage our network to do
That's
things
one of the
like,
functions that's being learned, is that?
yeah.
Okay, I thought you could determine it before.
Yeah. So an interesting question we can ask then is, how do we encourage this to be a rotation that actually normalizes our data? So no matter what kind of input I apply, I'm rotating by into this normalized representation for inputs that aren't. Okay. Yeah, so you can see here, this is G, this is H. Do you have a question? Sorry. Okay, I just went over this. It is G. Thank you. I forget who said it was G, but good job. Yeah, so now let's go over these symmetries from earlier. So rotational symmetry. Does anyone think that this is invariant to rotations? Okay, it is not. Kind of clearly, you can imagine it's rarely actually going to be. You can fix these weights as whatever you want in order to break this rotation invariance. So we can speed through the next ones. What about these? Yeah? Why?
I think because each point cloud is pretty together. And yeah, it's kind of interesting.
Right. So this is not so much can we learn scale invariance, but more is this always scale invariant? So if I scale all of my input vectors, could I possibly get something different if I have a bunch of affine transformations? Okay, I'll give you a hint. Let's say H is the identity. Even though n gets mapped, even though we're mapping from 3 dimensions to 1024 dimensions, let's say it's the identity where we preserve our first 3 coordinates in this vector, then we make all the other coordinates 0. Is it possible that our network could learn something like this? Yeah. Is that scale invariant? Yeah, so if I multiply a bunch of things by 2, then my max is going to have everything multiplied by 2, element-wise. And then softmax, unfortunately, is not a scale invariant function. So this would not be invariant to scale. And you can make similar arguments for rotations and reflections and translations. So these are actually not.
Well, you just mentioned that like the function learns, like the model learns the like affine transformation functions in each step.
Yep.
And like that's supposed to normalize data to be.
Yeah.
So on the pattern.
Well, the question we're asking here is, it would be really, really nice if our model was able to perfectly learn that. But we're kind of asking, even if our model kind of goes wrong and doesn't learn that, is there a case where our invariances might break? Right. And the reason we structure the network this way is because later on, you'll see that there's some tricks we can use to not guarantee these things, but encourage them to the point where they work very, very well empirically. They kind of appeal to our intuition. Yeah. Last one we'll touch on is is the permutation invariance. So did anyone see?
Yeah.
No. Can anyone say why? Right. So let's break this down just block by block. So if I have a multi-layer perceptron that I apply to n points and I apply it pointwise, is that a permutation invariant function? Maybe I'm phrasing this poorly. So if I am just applying something pointwise, so I apply this multi-layer perceptron to each point individually, and then I permute that. Is that like permutation invariant? Is it something else? So it would be a permutation, what we say permutation equivariant. So the permutation I apply to my input is the same permutation that I get in corresponding output. Is that clear to everyone?
Yeah, it's like,
Yeah.
on each one, I think that's specific.
Yeah.
Content, not be that same.
Yeah. So what all that means is, let's say I apply some permutation to my input, and then I apply this function pointwise. It's the same as applying this function pointwise and then applying the permutation after.
Yeah.
That clear to everyone? Right. So if I have a bunch of functions that are permutation equivariant, and then I feed this into something that's permutation invariant, what kind of function is that?
Should be maybe.
Yeah. Does anyone see, do other people see why? So, okay, maybe I should, do we have a marker? How should I say this? I'll give an example with 3 points. Let's call them A, B, and C. And let's say I'm going to have some function f, not related to our f from before, which is some function f. So if I take f of, and this is going to be like my n by 3 is just represented by these vectors a, b, c. So let's say I take f of a, f of b, and f of c, right? So I'm applying this pointwise. Let's say I take, I apply a permutation. So I first permute ABC into BCA, and then I take f of C, f of B, f of A. Is that the same as applying f to ABC and then permuting things after?
Yeah.
Yeah, that clear to everyone? Yeah, okay. So you can see here, if we have some kind of function that behaves this way, where it doesn't matter if we apply this permutation before or after, and then we apply this to something that's permutation invariant, so no matter its permutation, it's always going to give us the same output. This cascades and gives us a whole function that's permutation invariant. That kind of makes sense? And the reason why permutation equivariance helps with this is because it's saying that permutations here only permute our output. So if we have something that's invariant to the permutation in our output, but our output, like pairwise, is kind of still the same values, then we're okay. So this is why permutation invariance works. So this would be contingent on our feature transform being permutation equivariant. Right. So, okay, if we have no, 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 and yes, if we do things right in the TNet, what's the whole point of this? So you guys have kind of been asking this the whole time, and the whole point is to use some tricks in order to get our model or encourage our model to learn these things. We're not going to guarantee them, but we'll see in practice that it usually works very well. All right, so the first kind of transformation, the first kind of trick that we can use is regularization in our loss function. So does anyone know, or can anyone guess or tell me why we would want to add this term? So what's very, very interesting is that if we consider all rotations in R3 and all reflections in R3, they're all characterized, all the matrices that do this have the property that if we take this matrix as A, we take AA transpose, we get the identity. Anyone heard that before? Does that ring any bells? So it's it's a rotation or reflection matrix if and only if AA transpose is equal to the identity. Right. So does anyone see where this is going?
And then of course, the rates should be like so transformation.
Right.
Yeah.
Yeah. So if we're doing a classification problem and we also add this regularization term to our loss function, well, one, we're encouraging our feature transforms right here. I'm not going to get into the TNet details, but we're encouraging the outputs, the pointwise feature transforms that we apply to all of these points to be rotation matrices, right? So if we have good training dynamics, well, we're going to want to minimize this. We're also going to want to minimize our classification loss. So what might probably happen in practice is our model is going to learn to take different rotated or reflected versions of our objects and kind of normalize them. So that photo that I showed at the beginning where I took all the objects like the chair and then slightly rotated it, ideally our model is going to be able to rotate everything back. Or if I have a different rotation, it's going to normalize that. Is that clear to everyone how that might be able to happen?
Yeah, maybe I think there's something, but like, isn't the dimension of a transpose would be like a square matrix? Like, how do we take a length from a square matrix?
Oh, so this right here, sub F is it's called Frobenius norm. So if we have a 3x3 matrix, we can map this to a 9-dimensional vector, right?
Okay.
Everyone see that? And then we can take the norm of that. That's equivalent to this. So it's like squared error, but for matrices instead of vectors. Sorry, I shouldn't have touched on that. That clear to everyone?
Yes.
I think, yeah, it's called Frobenius. But although in the paper, I think this F might be something else, which is kind of funny. It should be Frobenius. Yeah.
Look at this. Take like what you said here and this. Look at this on the optimization function of that. So, but this if you project it to a steeper manifold, then it will always remain in the functional space of that. In the
Yes, but I don't know if everyone's familiar with tangent spaces.
probably like that's the formula.
Yeah, but I don't want to go into minutes. We'll stay away from this.
So this A5 transformation, those two matrix, it's a set, so it's like a forward and a transpose.
So an affine transformation, like I said before, is going to be a linear function that's then translated after.
But is it learning that like universal for all the training data, or is it per sample that is it one function for everything?
No, so it's dependent on our inputs.
Okay.
Yeah. So like we said before, we want to design, without getting into the details, we want to design our TNets in a way so that it is dependent on inputs. We can perform affine transformations dependent on inputs, or else they would be kind of useless, right? Because intuitively we want to learn to normalize our data to rotate it or reflect them back.
So this is like, in a sense, a very complex normalization. Is that sort of what it's learning? Like,
I wouldn't say it's too complicated. It's probably
No, but I
the
mean,
easiest form of
it's,
normalization.
yeah.
Yeah.
An input dependent normalization.
Yeah, it is input dependent normalization. Like any normalization should be input dependent, if that makes sense.
It's just
right?
that this is in a sort of 3-dimensional space. That's.
Yeah. So if it helps, again, if it's more intuitive to you, you can think of it as 2 dimensions or 1 dimensions. Again, the 3 is not fixed here. It's just usually when we're working with point clouds, they're 3-dimensional.
Is it effectively like, is there a visual, like, is it sort of centering the point cloud? Like, what is it sort of doing? Like, is it finding some?
Yeah, so ideally, like I said before, what we would want is if we have our chair that's oriented this way, it would be able to find some kind of like canonical orientation. Or if I feed something in that's oriented this way, it should be able to rotate it like that. And then if I feed something in that our network hasn't seen a rotation of before, it should be able to extrapolate and still. Yeah. So this regularization term is kind of clear to everyone. Like maybe not on the details if you haven't seen this exactly before, or you're just seeing like rotations and reflections for the first time, but it's kind of clear why we would want to do this and why Pope's model encourages this.
So it's clear that a minimum will find it.
Sorry?
It's also clear that to minimize that value, we'll get closer.
Yeah. And again, this is a joint training objective. So this is not our loss function, but it's a regularization term that we add to our loss function. So ideally, we're minimizing this at the same time we're minimizing whatever test we're doing for the classification. Okay, so this is what we said here is ideally these terms are jointly minimized by some kind of normalization rotation. That's kind of clear to everyone? Okay. Right, so wait, I lost a couple of slides. Oh no. Okay, it's fine. We can talk about just noise. I'll maybe touch on scale invariance and translations if people have questions about it at the end. But these are a little bit harder. Translations, we can again get away with this by instead of having this be a 3x3 matrix, we can have this be a 4x4 matrix where we just concatenate a 1 onto all of our input vectors. Or sorry, this would be, yeah, I guess it would be 6x6 then. So we're going to concatenate 3 1s onto our input vector, and that would be the translation term for vector. So we would have 6 outputs. So 1 for just a regular linear transformation, and then 1 for the translation that we perform after. Usually in practice, how we deal with things like translations or scale invariance can be kind of problem specific. And the best place to start is not with your network, but applying some kind of normalization or preprocessing to your data set. So if I know there's some kind of bias in my data set where a bunch of things aren't centered, but I want to apply this to something where things are centered, I might have some just preprocessing to translate all of these things before I train my network. Same thing can be said for scale invariance. Again, if we're using this in the real world and we're sensing data like cars, ideally scale invariance shouldn't be a problem unless size of cars like doubles. So sometimes there's practical ways to get away with this. Okay, so next we can touch on this thing called universal approximation. So one interesting thing I glossed over that you'll find in the paper if you go and decide to read it after this is has to do with the space of symmetric functions. So we know that what we learn here is symmetric function, like symmetric, it's permutation invariant, right? If we design it correctly. So here's an interesting question we can ask is, can our model like sufficiently approximate any permutation invariant function? That's something you can ask. Is our model expressive enough to do this? Maybe is there a permutation invariant function out there that our model can't closely approximate? So the answer is actually no. The authors showed this in the paper. It's interesting, and the math is surprisingly simple. You can actually show that this would be able to learn any permutation invariant function. Right. So another interesting result that we get from this is they make some argument about the continuity of set functions, where if you have slight perturbations in your points, this shouldn't affect your output too much. This, of course, is not a very good argument because these perturbations could be like below numerical precision on a computer. So like mathematically, this doesn't really hold up or tell us anything interesting in practice. We might want more clever way to analyze our network. So one way the authors do that is with this theorem right here. So you go ahead and just read this for maybe like a minute. It's fine if you don't understand anything whatsoever, but just try to read it. I also try to rewrite it in some English if you forget some symbols from your courses. Right. So this CS and this NS, does everyone kind of see what this is doing? It's saying we can pick a collection of sets where for any sets sandwiched between this CS and this NS, our function will always output exactly the same thing. So, okay, just to give you some geometric intuition, the authors actually, they show this in paper. Here is CS that you're seeing before is what they call a critical set. And do I want these? Yeah, these ones are better. So here's some geometric intuition for this theorem. Is let's say this right here is our CS, and this right here is our NS, and this is some set in between. What's saying is if we take any subset that's a superset of this set and a subset of this set, our network is always going to output exactly the same thing. So the authors actually show some of this empirically, and they compute some of these sets for us. So you can see we have this very sparse set right here, and this other set right here. And if we take any superset, any subset of this, our network's always going to output the same thing, which is some nice geometric intuition. So this is, I'm going to gloss over this because, well, I don't want the pizza to get cold, but you can go ahead in the paper, and I would say don't be too scared of the theorems and what they might be able to say by noise invariance, because usually if you're able to just dissect these symbols and write it out in English like this, then you relate it to some of the figures in the paper, you can see they're actually saying very like simple, interesting things geometrically. Right. So there's still some problems and some things that we can't totally prove in the paper, like this invariance to noise. These slight perturbations things is saying, okay, ideally, if we have some set and I start removing a couple of points in the set, I should actually get exactly the same output like we just saw. And slight perturbations, they also make some arguments for why if we slightly move some of these points around, since we're working with a max function, it actually does nothing at all. So you can imagine if we want to have some pre-processing, like some basic algorithms to get rid of outliers, you can imagine if we accidentally remove a point that's not an outlier, maybe this would be a nice argument to say that, okay, hey, we're guaranteed that absolutely nothing happens. So as you go and read the paper, I would encourage to actually focus on some of these theorems and then try to see if you can find a figure in the paper that relates to them. Because like this one, the authors do a really good job of giving some geometric intuition for how this works. And you can start reasoning about some of the other invariances we talked about and thinking about some noise invariants that we talked about before. Okay, so now I'm going to wrap up. And we talked all about classification. But there's also segmentation that we talked about before with this kind of binary matrix, or this matrix of probabilities that we might have. So how can I segment my scene into m classes for each point and find what it corresponds to? So if you were able to kind of understand the classification network, of course, it hasn't been too long, so you'll just need to read it once or twice more and then should solidify a lot of your understanding. You should be able to read parts of the paper that talk about the segmentation network. Essentially, what the segmentation network is doing instead of our classification network is our classification network aggregates everything into some global vector that we then use to classify our network, because we're classifying an entire point cloud. So the whole thing is a chair. But segmentation, we have some of these local properties. So for example, I might need information from the entire scene to tell that something's a tree, but I also might need local information local to that part of the scene to tell that this particular point is a part of a tree. So some intuition for what's going on here is they come up with some kind of design that intuitively says, okay, we have this thing that collects global features that we steal from our classification network. Then we do some local stuff. And then with this local and global information, that's enough to sufficiently segment. Okay. Something else that we can touch on briefly is how can we do better than aggregation? So we have some tricks for not losing too much information during aggregation, like mapping to higher dimensions before we aggregate. But maybe is there something better? I know we had something like this theorem that the authors have that says that we can approximate any permutation invariant function, but maybe we can do a bit better than this. I don't know. Maybe even though we can come up with weights that actually approximate any permutation invariant function, maybe this doesn't actually happen in practice. And there's some issues with training dynamics that cause this to not work too well. Another thing we can ask is, how do we attend to other points? So if I'm doing something like segmentation and I want to classify a certain point, I don't want to just have local information to this point, but I want local information with, say, the 10 closest points or something to be able to say what this is. Maybe if we want very fine-grained segmentation. So maybe we can use something like attention. What's very interesting about attention is before we talked about softmax is actually permutation equivariant. So you permute the inputs of softmax. It doesn't matter if you apply the permutation before softmax or after softmax, you get the same value. So what's really, really interesting is you can actually show that if any of you are familiar with transformers, if you remove positional encoding, this attention computation becomes permutation equivariant, which is very interesting. So we're able to collect information about nearby points and attend to them in a permutation equivariant way. Just something to think about. And then lastly, I just want to return to some of my points before we even talked about learning on point clouds. Are there any invariants that you think we missed in this paper or that aren't addressed? And how could we tackle things like sparsity or partial observation? Maybe intuitively, this is not an invariance or an equivariance. We talk about it in a very mathematical way, but you say something like, I take my point cloud and I chop it in half. I want to still be able to classify that. How can we go about constructing a network that can do that? How can we go about transforming our data in a way so that this works? Something interesting that we should think about. And also relates to some of these problems like sparsity or partial observations. But which of these problems don't even need to be solved with our learning algorithm? If I'm working with a LiDAR sensor, is it better to spend my time improving the sensor, or is it better to spend my time improving the learning algorithm? Something very important to think about. Okay, and that's all. Thank you.